welcome everybody to the August 2023 meeting of the Mornington Peninsula Astronomical Society, and we're kicking off just about exactly the same time as the match is up in Sydney with the Matildas. Shown here are some of the things that have happened recently to do with astronomy. So top left we have OceanGate's co-founder, and if you remember the name OceanGate, they were the ones that didn't quite so successfully send the submarine down to the Titanic a little while ago. They actually have drawn up plans to colonise Venus by putting 1,000 people in pressure chambers on Venus. But you'd have to say, well, what could go wrong? So shown there is the surviving co-founder. The other one didn't quite survive, and whether or not that comes to fruition remains to be seen, but they've set up the organisation for that. Over on the right-hand side we see one of the best images, I think, that's been captured by ASV member Kevin Burford from up in Melbourne looking south. You can just make out the Southern Cross to the bottom right of the camera image that he shows there. This was on the 7th of August, the Russian third stage rocket that re-entered over us, and you can actually see the path. If you look at the bottom right on the map of Australia, the final path is shown by the single orange line where it actually ended in the Tasman, and the predicted area where it would splash down or hit land was shown in the rectangle, so it was pretty much to the extreme western side of it. You can see it coming in there from the west, looking southerly direction and heading over to the east where it would land in the Tasman a few moments later. So pretty spectacular and caught very well in that image. Shown in the middle bottom section there is a Bronze Age arrowhead has been found to actually be composed of a meteorite. This came from somewhere around about 900 BC, found in Switzerland, and one of the few examples of them importing a meteorite for making such weaponry. And over on the left-hand side, from one of the large telescopes in the Atacama Desert in South America, they've detected two exo-Trojan planets. Now, what the Trojans are in our solar system are the asteroids on either side of Jupiter's orbit, so they share the same orbit as Jupiter. Exo-Trojans are two planets orbiting around the same star, sharing the same orbit, which is unusual. So it's pretty much, you can think of it as the situation where we had Theia collide with the Earth, the proto-Earth, to actually knock us over on our axis and rip out the moon. That would have shared a very similar orbit to ours, and they've actually detected it on this star called PDS 70, which is about 370 light years away. And as you can see, they've directly imaged two stars in the middle there. They've sort of kindly drawn the orbit and the two planet bodies that are shown there. So tonight we'll, as usual, go through the events past and coming month. Then we'll look at Sky for the month. Now Guido's not able to be here. He's on the way to America to the Jet Propulsion Laboratory, but he's kindly sent in Sky for the month by video, so we'll show that. Followed by Chris's Astromofo challenge. Then we'll talk a bit about the field trip to Loch Sport by Nerida and Dave. And then we'll look at what is reality. This is only a fairly short documentary, goes for about 30 minutes, looking in one of the contenders of a theory of everything, explaining what reality is in the universe. Then afterwards we'll look at three shorter videos each go for about 10 minutes each. One is to do with the Arecibo radio telescope. That was the giant dish that collapsed catastrophically not too long ago. But it actually sent more than one message out into space many years ago, and this is one that you may not have realised had been sent. I certainly didn't. And it has already arrived at its destination where it was sent, the star system. Then we'll look at the crawler, the giant crawler that they used originally in the Saturn V days to transport it out to the launch pad, and they still use exactly the same crawler today for taking things out to Cape Canaveral with that. And we'll take you inside, look at some of the engineering of that. And then why do the exhausts that come out of rockets actually look the way they do? And then we'll close with something that actually demonstrates some of that with a New Zealand launch. So, recent events, we've had a few in the last month, aside from the Working Bee up here where we had the Astronomical Society of Geelong come and visit, which was a great Saturday night, and were very, very successful, and we will no doubt return the compliment and go visit them sometime as well. A couple of days later we had the Hastings and Tyab Scouts and Cubs come here to the Briars, followed by the regular Scout Cubs and Guides night a few days later, which had lots and lots of different packs come from ranging up from Beaumaris out to Narrow Warren and down to Rosebud, so they came from far and wide for that one evening. Then we had the Devon Meadows Cubs, who were a boisterous group, come here for an evening on a Saturday evening as well. And we had a committee meeting on Zoom where we talked about several things. One obviously is Vastrock, and decided to kick off the advertising for that, and also looked at introducing gift certificates and cloth badges. Now the gift certificates are active, but the cloth badges I think are still on the way. Yeah. Then on the 4th of August, Guido talked at the public night here at the Briars, and they fortunately were able to see something through the cloud despite the it not being so kind in very distant suburbs, or those suburbs too far away from Mount Martha, so we were quite fortunate that night. And then last night we had here the National Indigenous Space Academy with Guido. You can see him at the back, third from the right. With his Indigenous students there that are off to the Jet Propulsion Laboratory with him as part of that sponsorship by Monash University. Coming up soon, very, very busy month, as you can see by all the writing on this particular slide. Starting this Friday, we've got the National Science Week Public Stargazing night, and at this stage we're full. We've got at least 95, it may even be up to 97 now. Booked for that one. Trevor's going to be speaking this Friday. Working Bee is then on the following Saturday, and committee meeting will be the Tuesday afterwards by Zoom, not the Wednesday. Then over a week after that will be Strathmore Girls out at Merrick's Lodge. We've done them a few times, and they keep asking us back for more, so we must be doing something right. 1st of September, public stargazing night as usual. Again, we've got a lot booked for that one as well, 97 booked. That's, of course, not everyone turns up, particularly in this weather, and people get sick at the last moment, so Manfred will be talking there. Then the first couple of weeks of September, we've got 2 nights for Tour 8 girls. The first will be on the 5th of September here at the Briars. We've then got a guides group which is actually being held out at Berwick. Now I believe Berwick is probably next to Narrow Warren, isn't it? Yes, not far from there. And that was 30 girl guides out there, so we'll be going out to visit them for the first time. Then the second Tour 8 girls later in September, and followed by the astrophotography workshop. We've got 85 booked, which I think is the capacity we've set for that workshop, so that's now full. After the next monthly meeting here, we've got the TLD, the Telescope Learning Day, and we've got 50 booked for that, which means we've only got 10 vacancies left for that one at the moment. And then followed afterwards by Vastrock in November, and we're currently about 1/3 to one quarter to 1/3 of the tickets have already gone for that one, or the seats have already gone. Now, Sky for the month. Last month we beamed Mark Stevens out, and this month we're beaming in Guido.
Welcome to Sky for the month for August and September 2023. Let's have a look at the planets first. So this is a view of the solar system from above. So all the planets are going counterclockwise around the sun in this view. And as you can see, as seen from Earth, the evening sky, or the west, would be towards the bottom of the screen here. And the morning sky, or the east, would be towards the top. So what we can see here is that Venus is currently in the morning sky, and this is a view of the solar system around the 1st of September 2023. And Mercury and Mars are both still in the evening sky here towards the west. And we'll have a look a little bit later what that means for how they travel through the solar system in this month and the next month. So zooming out a little bit, if we zoom away from Earth and the inner solar system planets, then we can see the orbits of Jupiter, Saturn, Uranus, and Neptune, the outer planets. You can see that all of them are pretty much in the same region of the sky at the moment, and all in our evening sky. So all of those planets are visible at the moment, and we'll see what they look like in a minute. All right, so let's start with the innermost planet. So this is a view to the south, and now we'll just zoom in towards the evening sky at around 6:30 p.m. on the 1st of September, and Mercury will be very low in the evening sky. We will probably not be able to see it from the Briars at all, because it is now moving into inferior conjunction. So inferior conjunction means that, you know, Mercury is still a little bit behind us in its orbit around the sun, but because it's an inner planet, so closer to the sun than the Earth, it is moving faster than us in its orbit. So it's moving in between us and the sun at the moment. It will be in inferior conjunction between us and the sun on the 6th of September. So obviously around that time we won't be able to see it at all. But it will then, because it's going very fast around the sun, it will then reappear in the morning sky and move into its greatest elongation west as a morning object around the 22nd of September, and appearing at around magnitude 1.5. And it should be visible then, but it'll be relatively low in the sky. Okay, zooming out a bit again, let's have a look what else is in the sky in the early evening. So you can see here that Mars is not very far away from Mercury at the moment, still a little bit higher in the sky. And if we zoom in on Mars, it's actually going to be relatively small in the sky and relatively low above the horizon in the western evening sky. And Mars is now approaching its conjunction in November. So Mars is further away from the sun than the Earth, which means that it's moving much slower, and we are racing ahead in our orbit. So that means that in November, the sun will be between us and Mars, and we won't be able to see it. It will then reappear in our morning skies in early 2024, but it'll take quite a while before we can actually view it again through telescopes later next year. So if you want to have a last look at Mars, this is now your chance. It won't look very spectacular at the moment because it's so low in the sky, but yeah, your last opportunity to have a look at Mars until mid next year. Okay, moving along. The next thing we will look at in the sky for September will be our moon. So on the 1st of September, our moon will sit over here in the Pisces constellation, and it will be just 2 days after the full moon on the 1st of September. So the second full moon for the month of August will be on the 31st of August, and it will be a super blue moon. So super moon just means that at the time when the moon is in the position where it's the full moon, it's also the closest to the Earth. It's at its perigee in its orbit around the Earth. So we will have a super moon on the 31st of August, and also a blue moon, which simply means that it's the second full moon in the month of August. And then, of course, about 2 weeks later, we will have the new moon around the 15th of September, and then the September full moon will again be a supermoon, so again at its closest point in its orbit around the Earth on the 29th of September. Okay, let's have a look at a few other planets in the sky. So we're now at around midnight on the 1st of September, and Jupiter will have just risen above the horizon in the east. So Jupiter is now rising around midnight at the moment, and it will start to rise earlier and earlier every day from now on. It's currently moving in a retrograde movement, which means that it will appear to move backwards across the sky. And that's, of course, just an optical illusion because the Earth is now moving in between Jupiter and the Sun. So we are catching up and then racing ahead, and that means that it will look like Jupiter is moving backwards. It's now moving towards its opposition with the Sun. So in November, Jupiter will be exactly in the opposite place in the sky as the Sun. So that's the perfect time of the year to view the planet because it will be at its brightest and at its closest to the Earth. In September, it will be around magnitude minus 2.7, so very bright, very obvious in the sky, and a really great time to view the planet. It's really fantastic to have it back in the skies for our public events, because that's always a welcome sight. The next planet out from Jupiter, of course, is Saturn. Saturn is ahead in the orbit, so it rises a lot earlier than Jupiter. So it's high up in the sky around midnight at the moment. It actually rises just after sunset around 6:30 or so. And again, will rise a little bit earlier every day. It's at magnitude 0.5, so also quite bright and very obvious when you know where to look. And it is currently moving towards opposition on the 27th of August. So on the 27th of August, it will be exactly opposite the Sun. So a great time to view Saturn at the moment through binoculars or even a small telescope. And through a small telescope, of course, you can see its ring system, you can see some of its moons, and that's certainly something to look forward to in the next couple of weeks. So you can see here that the rings are actually closing in at the moment. So every year at the moment, we are moving closer to the point in the orbits of the Earth and Saturn where we are looking edge on onto the rings. So in a couple of years, it will look as if the rings have disappeared because the rings are closing up. And in a couple of years, around 2025, we are moving through the plane of the rings in our orbits. And then after that, the rings will start opening up again in the opposite direction. When you look at Saturn around opposition, it's at its brightest because it has the most sunlight being reflected directly because it's immediately opposite the Sun in the sky. If you then wait a couple of weeks towards mid or the end of September, you can then again see a shadow being cast by the planet onto the ring system. So that's something to maybe try and take a photo of or have a look at through a telescope in September and maybe early October. Now I think I'm going to skip one planet here, but we'll come back to that one later. So the next one we're going to look at from this point is Neptune, the outermost planet of the solar system. So Neptune is relatively close to the moon in the sky at the moment on the 1st of September. It currently rises around 8 p.m. and it will be at opposition, so at the closest and brightest as seen from the Earth, around the 19th of September. So even then, when it's at its closest and brightest, it will only be about magnitude 7.8. So not very bright. You won't see it with the unaided eye. You will need a telescope for that. And even through a telescope, it will be obvious that it's a planet, that it's not a star, right? It'll appear as a small bluish disk, but you won't be able to see any kind of details in the clouds or anything like that. So you need far bigger and more expensive telescopes than what we have here at the Briars for that. But anyway, if you want to take a picture of Neptune, now is probably a good time around opposition. All right, we're now doing a bit of a fast forward to the early morning sky, I believe, so around 5 a.m. or so, in order to have a look at Venus. So Venus is currently, or especially in September, a morning object, and it'll still be very close to the Sun on the 1st of September. So it's past its conjunction on the 1st of September, so it will have moved away from the position between the Earth and the Sun. So we can see it again as a morning object. but it'll be a very thin crescent around the 1st of September. And then it'll race ahead in its orbit as seen from Earth and become brighter and brighter until it reaches its greatest illumination on the 19th of September. And by then it will reach a magnitude of -4.8, so a very, very bright morning star. Yeah, around the 1st of September, it'll be quite low in the sky in the early morning. Now, as I said earlier, we skipped one planet because I made a mistake when I set up the presentation. So let's zoom out again and move back towards Jupiter, I believe, because Uranus is also in that part of the sky at the moment. So Uranus currently rises just a bit after Jupiter, so also around midnight. And very similar to Neptune, you won't be able to see anything with the unaided eye. It's magnitude 5.7, so in really dark skies, and if you're probably a bit younger than me, then you might be able to see it if you know exactly where to look. But with a small telescope, you should be able to resolve a blue-green disk. Again, you won't be able to see any kind of surface structures or anything like that. So here you can see Uranus with its very faint ring system around the planet. We won't be able to see anything like that with any of the telescopes that we have access to, but you may be able to see, or at least photograph, some of its moons. And you can see here all the moons around Uranus are named after Shakespeare characters. So it'll be around magnitude 5.7, as I said. And it's currently also in retrograde motion. So we've basically just passed it in its orbit. And that's why it will appear to move backwards against the background of the stars for another 5 months. All right, so just as a summary, this is what the planets will look like if we looked at them through the same telescope with the same kind of level of magnification. So you can see Venus is very close to us at the moment because it's basically between us and the Sun. So it will appear very large, but at the same time only a very thin crescent will be illuminated. So not very much to look at through a telescope. Mercury, you can see that is very dark, so again, very thin crescent, but it will move away and into a much bigger illumination very quickly in the middle of September. And then Mars moving very low towards the horizon now, and not that spectacular to look at even through a telescope. Jupiter and Saturn are now in the perfect position to view them. You can see that they will appear quite large through a telescope, so even a modest magnification will resolve quite some detail in the clouds. So you might be able to see the Great Red Spot, you might be able to see some moons transiting and so on. So have a look out for any updates on E Scorpius, for example, when there are special events happening around those two planets. And yeah, Uranus and Neptune, just small blue greenish disks if you want to have a look at them through a telescope. There's a couple of other things in the solar system at the moment. So here's a list of comets. I don't think any of them are particularly interesting at the moment. So we've got 103P Hartley 2 rising after midnight, but very low in the northern sky. Magnitude 10 maybe increasing to magnitude 8, but yeah, it's pretty faint and very low in the northern sky. So unless you live north of Melbourne, probably not worth looking for that one. And very similar with Comet 2P Encke, also rising around 3 a.m. So you have to get up early or stay up late. It will move through a couple of constellations, but also towards the north, also around magnitude 8. Then we have the two Pan-STARRS comets. Both of them are now only magnitude 12, so you would really need a telescope to get a photo of them. K2 Pan-STARRS rises around midnight in Monoceros. K1 Pan-STARRS is a circumpolar comet now, so it doesn't set. And you can just look towards the south celestial pole, but again, it's only magnitude 12, so probably not something worth taking a photo of at the moment. And then the last two, V2 ZTF and T4 Lemon, we had some nice pictures of those earlier, but now they're both fading. So V2ZTF is now rising around 9:30 p.m., but it's only magnitude 10. And Lemon is now fading towards magnitude 12 and setting at 11 p.m. Early in the month, and then at 9 p.m. a bit later in Libra. So probably not the best time to go comet hunting at the moment. So let's have a look a bit at the sky in general. So this is looking towards the south. You can see the familiar constellations. So we have the Milky Way stretching across the sky here. We have the Southern Cross and the 2 pointers around here in the southwest. And then the usual nice deep sky objects like the Carina Nebula, for example, is getting a bit low in the sky at the moment. While the Small Magellanic Cloud starts out a bit low, but then actually has quite a nice position in the sky for viewing a bit later. So as you can see, as we move from around 7 p.m. Further towards 8 p.m., 9 p.m., the Small Magellanic Cloud starts to get up a bit higher, and with it, of course, the fantastic globular cluster 47 Tucana. So that's a really great target for the next month or so. You can see that a bit later in the evening, around midnight, the Large Magellanic Cloud is also coming into view, while all of the Milky Way is starting to really get very low towards the horizon. And then in the early morning, you can see a few things coming up in the east again, like Sirius, for example, which we haven't seen that much of in the last few months. Looking towards the northern sky, we can see the constellation of Sagittarius in a very nice position to, for example, do some astrophotography of the Lagoon Nebula, the Eagle Nebula, those sorts of targets. So that constellation is now moving across the sky. So we're now around 10 p.m., 11 p.m., but it's still in a reasonable position. Then after that, you can see the planets coming through now, Saturn, and then the Moon and Jupiter and Uranus tracking across the sky. So you can see that that's kind of the plane of the ecliptic where it sits in the sky at the moment. And then in the morning sky, we can now see an old friend reappear. So Orion is now rising before sunrise again. And that's, of course, a sign that we are getting closer to summer. So that's all for Sky for the month for August and September. I hope you found some nice targets for visual observation or some astrophotography. And hopefully there's something in there that you can use for next month's AstroMOFO challenge as well.
Welcome to AstroMOFO for the month. Okay, the last challenge was planetary nebulas. So planetary nebulas are the leftover remnants of stars that have reached the end of their lives between about 0.8 and 8 solar masses. They come up to a stage where they have high energy fusion in the core, blows out the sun into a very big size. The energy from the fusion going on blows the outer layers out into space, and what's left is the beautiful nebulas, planetary nebulas that we see, and what remains at the center of that is a what's called a white dwarf. So it's a dead star which isn't fusing elements anymore and is just slowly cooling down until the end of time. This image here was caught by Kelly Clitheroe from Geelong, who's also a member of MPAS, and it's M27, the Dumbbell Nebula, which she captured with her 107 mil TS optics and L-enhanced filter. Okay, now the next one that we've got, okay, so this challenge was completed by a few of us, Greg Walton, Kelly Clitheroe, Dave Rolfe, Phil Peters, me, Chris Costa-Canellis, and a late entry by Chris Black as well. And here we've got the Bug Nebula by Dave Rolfe, NGC 6302, captured with his, I'm assuming his William Optics 132. Yep. Okay, so planetary nebulas are emission nebulas, which means the gas that we see glowing from them is emitting light. It's not reflecting light from the star. So the heat from the the star in the middle of it has energized the gas and has caused them to, causing the gas to emit, re-emit the energy. And that's why some of them, they're better caught with these dual band filters that we get. So the Optolong does a pretty good job of filtering out a lot of the light pollution, and it gets a lot of the emissions, the HA and the O3 emissions from the nebula. And these are my photos. So we've got the Ring Nebula, which was pretty low in the sky, in the northern sky when we captured that, the Bug Nebula, and also the Helix Nebula. So with just varying amounts of exposure, and these were all captured at the observatory here with the 127mm refractor. Next, we've got a whole bunch of images here captured by Greg as well with the equipment down at the observatory too. So we've got the a couple of them with the 127mm refractor, which are M27. Let's have a look. Should have a pointer. Do I have a pointer? There we go. Okay, M27, the dumbbell over here. The Ring Nebula M57 down here, which were captured with the refractor, and the rest of these were captured with the Meade, weren't they, Greg? Yeah. So we've got the Spare Tire Nebula up here, the Helix, the Saturn Nebula, the Blue Planetary Nebula, the Bug, and the Spiral. So this one's actually quite faint. It's actually a pretty tricky one to capture, but Greg's got it all there, all with his Pentax DSLR. Phil also managed to get some shots as well. So we've got the Blue Planetary Nebula there, the Cheerio Nebula, which is a really faint one. That's a pretty difficult one to capture. So it's in the, hang on, yep, just in the middle over there. It's called the Cheerio because it resembles a little Cheerio chip that you could buy, the little round chips, and the Spiral Nebula here as well. So they're all captured by Phil with the 8-inch Newtonian here at Briars as well. So if you are thinking of getting involved here, you can easily come down and use the equipment here, and Greg or someone will be able to give you a hand. If I'm here, I will, but by all means, feel free to get involved. Okay, next one was a late entry by Chris Black, who managed to get this one of the Helix Nebula. So this is actually with a pretty small telescope, a Red Cat 51, which I think has only got about a 300mm focal length. So it's a pretty wide field of view. The Helix is actually one of the bigger nebulas that we're able to see, planetary nebulas. So it's a pretty good one to be able to capture, and it's quite bright as well. So you got this with his Canon 6D and 45x90 subs to stack to get that one. So he did say this was a challenging one because he's got a small focal length telescope with a full frame camera, which makes the nebula appear quite small in the field of view. But he said that was all part of the challenge and part of the fun. So good on him. Okay, now the next one will be, as Guido said, we've got a blue supermoon coming up in a couple of weeks. So the moon's going to be our next MOFO challenge object. So you could pretty much capture this with any sort of photographic equipment you've got. So we're expecting to see a lot of photos of this. If you want, try and get some finer details on the surface, or maybe get some nice landscape photos, the moon rising or setting or something like that. So that'll be our next one. Now I do have to say, I don't know if anyone's been sending emails to my email address here, but it was misspelt. I misspelt my own name. So if you were sending them by email and they weren't coming through, it's because of me. And that's it. That's AstroMOFO. Thank you. Any questions? Good. Which one? The Ring Nebula. That was. I only got about 3. The Ring Nebula only got about 3 shots on it. The Helix. The Helix was around about 9 minutes, I think.
But was it a single shot or?
No, it was stacked. So it was. Oh, hang on. Yeah, 9 minutes. These were only 60 seconds. I was only able to get 60 seconds on each shot on the refractor because it wasn't tracking very well and I was getting a lot of streaking. So I had to, and with the Optilong filters, with the dual band filters, you do really need longer exposure times to get the enough light to come through. So that was only with 9 exposures. The Ring Nebula was only 3 exposures because that was pretty low. We thought we'd be able to shoot it through the door of the observatory at one point, but didn't quite line up. But that was pretty low, and yeah, the bug I got some good time on, so that was about 20 minutes worth. Yeah. Okay, thank you very much.
So this is a continuation of our tourism promotion in East Gippsland. Dave and I went to Locksport a few weeks back, and we were there for a Friday night and a Saturday night public viewing. The Friday night was actually all locals, about 100 people. Yep. And then the Saturday was all visitors to the area, but not locals. So this is the house I stayed in. They put me up in accommodation. I stayed at a Airbnb. Dave stayed at his parent-in-law's holiday house down there. Yep. So I shared with members from the ASV and from the Latrobe Valley. So this part's all about me because Dave's not here. Part of my view from the deck, the view outside my window. It was a pretty nice location.
Oh. You can talk about this. Okay, so this is at the... This even work? No. This is at the RSL Club. We went for dinner the first night. So the packages they do up there for the viewing nights, actually, you get a dinner and then you go out for viewing. So it's all part of the deal. That was all of us volunteers sitting at the one table here. We had Landon down there and myself at the end. I can't remember all the names. Steve Thurm.
Frank, me, Landon, Dave, Steve, Gay, Susan and Steve.
There's me at the end. There's some kid sitting next. Oh, that's mine. Right. The first night, it worked out cloudy. It was clear right up to the day, and a cloud came over just as it started. So I actually had prepared one of our PVN nights, and I pre-prepared it in that's what I said, Plan B. Stripped out a lot of the normal content and sort of ran through that, and I got probably 2/3 the way through the talk and it cleared up outside. And there I got some random shots here. Random shots. Landon just refused to wear long pants and a jumper, so it was freezing cold. There we go, we got some clear skies there. They were quite good up there. Nice and dark. Once it did clear, it was actually really good viewing. And they had a fire going and had a band too. I think there's another picture coming up. So they were sort of playing there behind the curtain there, and the locals were actually doing line dances, and it was something else. Oh, that's back to you.
Yeah. So the next morning, that's my bed, that's my view out of my room. It was hard to get up that day. And then Dave and I and Landon decided to go to the beach. Dave had his dog, Obi. Is that his name? And we're driving over this bridge, and Dave said, if you look out there, you'll see Loch Ness. I thought he was talking about a bay or something. And I took a picture, and I zoomed in, and that's Loch Ness. So we went down to the beach. It was a beautiful day, and there was nobody there. We walked past some people fishing, but this end had no one at it. Landon thought it was warm enough to swim in June in Gippsland. But it was a stunning beach. Obi. This was looking towards Lake Victoria. So where the Locksport is, you got Lake Victoria on one side and the ocean on the other side. So my accommodation looked out to Lake Victoria, and then you drove over to where Dave's side was, and you're closer to the ocean. Yes. This is Steve Thurm from the ASB.
Oh, Steve, yeah, he was he's head of the outreach for the ASV, so he came up, and his wife. I don't know. Oh yeah, and there's obviously kangaroos there. There's Chris Morley, he's president of Latrobe Valley. Stephen Gay. Now they're from also they're ASV, right? Yep, I got it right. Hey, there's me. So I took my binos up there. They actually work quite well.
And we had lots of kangaroos.
And obviously we're viewing on the golf fairway, so.
Oh
yeah. You can do this.
We got clouded out again the second night. So Steve Thurm from the ASV, first we had dinner actually. This was the golf club, which was next door to the RSL from the previous night. So first we had dinner in here, but we were clouded out. So then Steve has set up the projector and has done a stellarium style sky for the month, wasn't it?
Yeah. Something like sky tour.
And then Dave with all his mates.
Yeah.
It was cloudy outside. We were waiting for it to clear up so that we could tell everybody to come out.
I was spotting to make sure there's a gap will straight out. So.
That was the band hanging out with Dave, and then it cleared. So a lady's looking through Dave's binos. She had permission to put her hands on there for the photo to steady herself in the dark. Some of these photos aren't great because we had to borrow some from their local notice board at Locksport because we didn't take many ourselves of these nights. So that's someone who took a photo of my telescope.
That was actually from the golf club. I'm a member of the golf club up there, so they posted photos on the golf club page. So I snaffled a few of them.
That was really dark.
That was. I thought we had some videos of the band and dancing.
Yeah, it was so awkward.
Okay, because it was like a comedy show.
Right.
Oh, here we go. That was it for Locksport. So while we're talking about collaborative projects, the next one we're doing is Mount Buller Star Fest. It'll be January 5th to the 7th. So there's a public viewing lot up there. So Mount Buller are trying to promote, and a few other the parties, the Park Victoria and so on. I've got a grant to try and promote the regional tourism up there as well over the non-ski season. So there's a star viewing event up there, 4 nights I think, 5th to the 7th. That's going to be set up, and once again we're going to do that with a few societies. There's us and ASV are going to coordinate it, and we're hoping to talk to Langata and maybe Albury-Wodonga. In September we're going there, September the 8th and 9th was it? 7th and 8th, we're going up there for a pilot program to test what the viewing nights would be like. We've got about 80 or 90 people coming to that already, so there'll be 6 of us up there, a few from MPAS here, ASV, and Geelong will probably send 1 or 2 over too, so that'll do the pilot, and then that'll work out how we do this event, and hopefully they'll be doing 1 or 2 of these a month afterwards, as well as, hang on, no, go back, we haven't finished yet. Sorry, Mount Buller too also got a grant up there to build a observatory either on Mount Buller or Mount Stirling, so they got the funds sort of set aside on a big grant for that. So there's still to be a lot of details to be worked out, but essentially it'll be built, and there have to be members from astronomical societies around to help run and use this equipment up there, which will hopefully be remote access as well as for public viewing nights up there. So that's TBA how that's going to work, but it's pretty exciting. It'll either be Buller or Stirling will actually get that observatory. I think it's just one at the moment. They got a grant up there. I think I saw 50 or 60,000 or something to get started, and then I believe the project will be remote access, but they obviously haven't got the people up there to know how to run it. So they'll be we're trying to do this as a collaboration again between all the societies to help manage it and get it off the ground and do some viewing nights. But there's still early stages for that yet. These things can take years to get going. Yeah, okay. And here we go, this one is off the ground now, and we'll have bookings up shortly. So after the Gippsland events, we're going to do the Gippsland Star Party. Dates are locked in, so at the Stockman's Camp, where Nerida and Guido went for the first of these viewing nights. That's basically, you can talk about this, describe the venue, but it'll be set up again with the three societies, ourselves, LVAS and ASV, to run. I don't think there's ever been any star parties, to my knowledge, in that region of Victoria, so we're trying to run it a bit similar to what Vic South is as our template. So that'll be pretty cool. Nerida, you probably already told everyone about the facilities there on the slide last time. So it's a bit of a caravan park. There'll be some powered sites, unpowered sites on the field. Oh, there we go.
The telescopes or the camping over here. The telescopes or the camping can go over here, and then there's also powered sites up the back over here as well. But this is actually a huge area, and in here also there's a telescope area, and there's like a big barn where they've said that they will put on a barbecue, including desserts and stuff like that on the Saturday night as well. So on the night of the 16th. Yeah. That's it. That's the end.
So for the next 30 minutes, we'll look at what is reality, care of the Quantum Gravity Research Organisation in the US, in Los Angeles. And it'll be presented by Marion Kerr, shown here. And this is, most people will have heard of things like string theory. This is known as emergence theory, and has some very interesting things in it. As I say, it goes for about 30 minutes. If you need to get up and go and have a look at the TV or something, or have a cup of coffee, please do so.
I want to tell you about the universe. What it is, how it came to be, what its building blocks are. I want to tell you how the future creates the past, which then creates the future. But first, I want to tell you about crystals. You might be surprised to know that a crystal isn't an expensive piece of glass or a chandelier in some fancy dining room. The word crystal simply means a pattern that is periodic. Look at this checkerboard pattern. See how it continues to spread out infinitely in each direction? That means it's a periodic pattern. So that's a two-dimensional crystal. This is another two-dimensional crystal. And this is another. You can also have three-dimensional crystals. By the way, this 3D glass is called crystal because its atoms are actually arranged in a crystalline pattern. So, see how I'm projecting this three-dimensional crystal to a two-dimensional image on the sand? See how the 2D projection looks distorted because of the angle of the projection? That 2D image also has a pattern, but it isn't periodic. So, it's not a crystal. But there's a deep connection between the 2D object on the sand and the 3D mother crystal. This distorted 2D pattern is called a quasi-crystal. A quasi-crystal in a certain dimension, in this case 2D, is a projection of a crystal in a higher dimension, in this case 3D. A group of physicists in Los Angeles is working on a new physics theory where a particular 8D crystal, yep, that's right, an 8-dimensional crystal, is projected to 4D at a very particular angle, which forms a 4D quasi-crystal. And from this 4D quasi-crystal, they derive a 3D quasi-crystal, which they believe is the fundamental substructure of all of reality. This 3D quasi-crystal has a fundamental building block, a tetrahedron, which is a three-dimensional equilateral triangle. The size of each edge on this shape is the smallest possible length that can exist. This is called the Planck length. It's 10 to the 35 times smaller than a meter. So you know how your TV screen is broken down into building blocks called pixels? A pixel is the smallest possible indivisible unit of the 2D screen. So think of reality as your TV screen, but in 3D. And think of the tetrahedron as a 3D pixel, the smallest possible indivisible unit of reality. The tetrahedra in the quasi-crystal combine with other tetrahedra using complex mathematical rules to fill up all of the space in the universe. Each tetrahedron only has a few specific states in which it can exist at any given moment. And because of the rules of how these pixels connect to each other, if one tetrahedron is in a certain state, this dictates the states of many other tetrahedra throughout all of space. But here's the weird thing. If a certain tetrahedron can be in any one of just a few possible states in a given moment, who or what chooses the state it should be in at any given moment?
Well, for such a choice to be made, we need to scientifically, mathematically, and logically bring in a new element into physics. And that element is consciousness.
If you're not a scientist, you might be surprised to learn that nobody actually knows the exact value of the speed of light. We have a close approximation, but not the exact value.
The closest we can get to measuring it has to do with the precision of our machines. But no matter how precise our machines get, we will never be able to measure the exact speed of light without a theory that tells us what it is and why it is. And none of the current physics theories do that.
Oh look, Professor Einstein, you look so cute.
So I look pretty here?
Yes, yes.
No, wait, that's my bad side. But if I go...
Ja, das ist gut.
What if I stick up my tongue like this?
Sehr gut.
Oh.
Our best physics theories, Einstein's theory of relativity, and quantum mechanics both use the speed of light as a starting point. In other words, they use an inexact measurement of the speed of light without explaining why it is, what it is, or why the universe even has a speed limit in the first place. We need a new theory.
And such a theory is what the physicists and mathematicians of quantum gravity research in Los Angeles are working on.
They call it Emergence Theory, and it will, really for the first time ever, provide an explanation for the speed of light and the other constants, such as Planck's constant and the fine structure constant.
Basically, what is needed is a theory of everything, a theory that explains the very fundamental aspects of reality. String theory, which once held a lot of promise for possibly being a successful theory of everything, has not made any successful predictions. And regardless of predictions, the theory itself isn't actually a theory of everything. It's just not, because it can't explain the speed of light or the other constants.
Quantum mechanics and general relativity, on the other hand, do make good predictions, but they don't explain the fundamental constants either.
Professor Einstein, why does the speed of light have the exact value that it does?
Well, to put it plainly, security!
So what clues does nature offer us for what a theory of everything should look like?
We've identified 7. Information, causality loops, non-determinism, consciousness, pixelation, E8 crystal, and the golden ratio. A growing number of physicists are saying reality is made of information. What does that even mean?
Well, information is meaning in the form of symbolism. A language or code provide this kind of information conveying symbolism. A very different type of symbol is one that represents itself. Geometric symbols can do that. A cube can represent love, if we say it does. Or it can represent, really with minimal subjectivity, itself. Could there be a language or code made out of geometry? What type of information would such a language express? Quantum physics theory and classical physics indicate that reality is made of information. And there's no evidence that reality is made of anything other than information. Many physicists agree with this, and many don't. But those that don't agree that reality is made of information have no explanation for what reality is, if it's not information. Gentlemen?
Reality is made of information.
Nope.
Yes, it is made of information.
No.
Okay, so what is it made of if not information?
Energy.
Energy is information.
That's stupid.
Energy is the potential for a particle to change its position. Potential is information. Energy is information.
No.
It's information. Then what is it?
Not information.
Then what is it?
Not information.
Reality is geometric. A geometric language in the form of geometric symbolism, the type of symbols that represent themselves, might explain how a geometric reality can be made of pure information. Information implies meaning, but what is meaning? Meaning is a comparison. That's what we do. But we do it so fast, we don't realize we're doing it. We look at something and we match it to something from our database. We say, that is a crosswalk. That is a building, not a crosswalk. That is a window, not a building. So meaning is the perception of something relative to something else. So therefore, meaning is subjective and requires choice. Can we get some dramatic music here? Because meaning is subjective, for it to even exist, it needs to be perceived or measured by some form of consciousness. Einstein showed how the past and the future exist simultaneously in one geometric object. So all time exists all the time. Let me say that again. All time exists all the time. I know that sounds kind of weird and unintuitive, but we have to kind of suspend our common sense. And accept that mathematically, and according to the best physics formulas we have, that actually makes sense. So, let's visualize the geometric object that Einstein spoke about as a block. Remember the tetrahedra, the building block pixels of reality I told you about? Now imagine the entire universe, everything, everywhere, in one frozen moment in time. Like a single frame in a movie. In this one frame, all of reality everywhere appears frozen in this one position. Let me give you an analogy. In a movie shot on 35mm film, there are 24 frames a second. There's no actual movement in a movie. There's just a sequence of frozen frames. Now remember how I told you about the Planck length of space, which is the smallest length possible? Well, there is also a Planck length of time, and it is much shorter than 24 frames a second. In fact, it's 10 to the 44 times shorter than a second. Okay, so back to our frozen frame of reality. The entire universe in one frozen moment, one frame. But instead of a frame in a movie, it's a frame in all of reality. Now, imagine the next frame. Each frame is different from the previous one, just like in a movie. See how all frames exist in Einstein's space-time all at once? Okay, now here's where things get really, really weird. We assume that the past influences the future. That's how we appear to experience reality. But when you look at this block, why would one side be the past and one side be the future? Why go left to right and not right to left? Why can't the future influence the past? Take away the names past and future if that helps you think of this concept. So what if the past influences the future and the future influences the past in an endless feedback loop? So then, the question is, which part of the past is influencing which part of the future and vice versa? And the answer is, all time is affecting all time, all the time.
Hi, I need a drink.
Is this even possible? Can me 20 years from now influence me now, just as I influence her? So can me 5 minutes from now influence me 10 minutes ago, just as me 10 minutes ago influences me as a baby, just as me as a baby influences me on my deathbed? This is too weird to even grasp, but everything we know says this is the way it is. Am I stoned? Okay, so if every moment is co-creating every other moment, both forward and backward in time, then reality would be this massive neural network spanning space and time. This type of network would have one even way stranger quality than anything we've talked about so far. It would be its own creator. But the fact that all time exists all the time does not mean that the future is written in stone, and we're some kind of programmed animation or something. That's what they used to believe, though. Years ago, it was popular to believe in the somewhat bummer idea of reality being a deterministic program playing itself out.
Light is scattered by electrons and is bounced off electrons.
The famous double-slit experiment ruled out determinism. Look it up if you've never heard of it. It's wild and is one of the cornerstones of modern physics. But for now, take my word for it. It ruled out determinism and ushered in a new era of non-determinism, or basically, free will. So, how does free will work? One of the most surprising discoveries of quantum physics is that reality only exists when it is observed. That literally, particles do not exist until they are observed. Famous physicist John Wheeler, he's the guy who came up with the term black hole, says that reality is made of information, which is created by observation. The observation must be made, he says, by something conscious. And Nobel Prize winner Frank Wilczek said that quantum theory is contentious and obscure, and that it will remain that way until someone constructs, within the formalism of quantum mechanics, an observer, a model entity whose states correspond to a recognizable caricature of conscious awareness. An entity, an observer. So Frank Wilczek is basically talking about an entity, not necessarily a human being or an animal, that is capable of generating information by observing and measuring. But what would that conscious entity be? Well, we definitely know that consciousness exists in the universe. I mean, at least in us humans, right? I mean, I'm conscious, you're conscious, he's conscious, I think.
I'm conscious.
Consciousness relates deeply to physics in ways not yet fully understood. In fact, consciousness is kind of like one of the least understood things in all of science. Nobody knows exactly what it is. Weird, right? So if reality is pure information, if everything, energy, matter, thought, if it's all information, then it becomes clear that reality deeply ties into consciousness in some way, as if the fundamental stuff of reality is somehow consciousness. Did consciousness and information somehow emerge in a causality feedback loop? German physicist Werner Heisenberg developed the first equations of quantum mechanics using a type of math called matrix theory. He deduced that space and time were pixelated into indivisible three-dimensional Planck-length units, just like the two-dimensional pixels on your computer screen.
It's good to be made of pixels.
The mathematics indicated this.
Mathematics. I love mathematics.
Your pizza, Professor.
And pizza. Oh, I love pizza. Especially pixelated pizza.
And interestingly, there was no solid experimental evidence for smooth, In other words, not pixelated space-time.
Pizza.
Not pixelated! Not pixelated! Pixelated!
We are not pixelated!
Not pixelated!
Yes, you are, morons.
Your mother is pixelated!
This is smooth.
There is no evidence of that. And the mathematics show it is pixelated, so it must be pixelated.
Oh, that's interesting. Bullshit.
It must be pixelated.
Bullshit, 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 bullshit.
On the other hand, most scientists agree that a length can be no shorter than the Planck length, which suggests reality is pixelated.
There is no length shorter than the Planck length.
That means reality is pixelated.
I'm not pixelated! I'm not!
Dude, you're kind of being a little like one of those people who deny evolution because they can't handle the fact their ancestors were monkeys. Are you a monkey? Huh? Are you a little monkey?
We believe that until a quantum gravity theory of pixelated spacetime is discovered, the issue will remain confusing for everyone. What type of geometric code would describe a pixelated reality? 80 years of smashing particles together in particle accelerators, such as the famous Large Hadron Collider in Geneva, have given us a strange clue. That all the fundamental particles and forces convert into one another. Like they literally transform from one to the other, according to a process called gauge symmetry transformation. And all of these conversions correspond to a shape. And not just any shape, an 8-dimensional shape. Now this shape forms a crystal. Now remember, crystals are periodic patterns of a certain shape, like that checkerboard is a 2D crystal made up of squares. So this crystal is of a particular 8-dimensional shape, and this crystal is known as the E8 lattice. To generate that 3D quasicrystal, the substructure at the pixelated fabric of reality, we project this 8D crystal to 4D. And then we convert that to 3D. Now, just like the basic cell shape of the 3D cubic lattice is the cube, the cell shape of the E8 lattice is an 8D shape with 240 vertices. We call it the Gaussian polytope. When the Gaussian polytope is projected to 4D, it becomes two identical shapes of different sizes. The ratio of their sizes is a unique number, 0.618, also known as the golden ratio. The golden ratio may be the fundamental constant of nature. It is a ratio that is fundamental to circumscribed equilateral triangles, and it's weirdly ubiquitous in the universe, appearing everywhere from the quantum to celestial scales. Ever so interestingly, it appears in black holes.
I don't want to fly into a black hole! I wish I never theorized your existence!
Okay, let's get serious for a second. Here are 3 quick facts for you science heads. The golden ratio is the precise point where a black hole's modified specific heat changes from positive to negative. And it is part of the equation for the lower bound on black hole entropy. The golden ratio even relates the loop quantum gravity parameter to black hole entropy. Why does this support the claim that the golden ratio is the fundamental constant of nature? Because a theory of everything must unite general relativity with quantum mechanics, and a black hole is where these two theories converge at their limits. Okay, so bear with me through some really weird math right now, and I'll reward you with some amazing footage of John Malkovich getting a pie in the face. There's a type of mathematics called matrix mathematics. No, not that type of matrix. Matrix math is the type of math that quantum physics uses in its formulas. Without getting too technical, this is an example of a matrix. A matrix is just a group of numbers that are arranged in columns and rows. And there's a certain amount of combinations for these numbers inside the matrix. Like if a matrix has 4 numbers inside it, there are 24 different possible combinations for those 4 numbers. Quantum mechanics uses matrices that are binary, so they only contain various combinations of 2 numbers. Each of these combinations of numbers has a value. It's called an eigenvalue. Some eigenvalues are called trivial. These are values like 1, 2, and 0. And some are called non-trivial, and those are all sorts of more complex-looking numbers. So, here's the interesting part.
Where's that interesting part? Oh, yes, here.
The highest probability non-trivial eigenvalues that show up in binary matrices are, ready for this, the golden ratio and -1 over the golden ratio. So we now see a deep link between black holes and quantum mechanics, because the golden ratio appears deeply in both black hole physics and in quantum mechanics. Okay. Good job bearing with me. So, here's your reward.
John Malkovich getting a pie in the face.
No, I don't want, no. But I'm not John Malkovich.
Pie!
The golden ratio appears to startling accuracies in many other ways throughout the universe, in scales both large and small. It is so prevalent that its existence simply cannot be looked at as coincidental. In the past, the appearance of this ratio has usually been ignored by scientists because they had no way to explain it. So interest in it was considered the stuff of amateur scientists. But now, for the first time, a rigorous quantum gravity theory is being developed, which predicts the golden ratio's existence, literally, everywhere. So what would a theory of everything look like that answers these 7 clues we just presented? Information, causality loops, non-determinism, consciousness, pixelation, E8 crystal, and the golden ratio.
So we think reality is a mosaic-like code or language at the smallest scale of reality possible, which is called the Planck length. Particle accelerator data tells us that all particles and forces relate to one another according to a higher dimensional crystal called the E8 lattice. But reality appears to be 3D. So we project a slice of this E8 crystal down to 3D, which produces a quasi-crystal code or language. And that allows these geometric symbols to build up to the ordinary world of particles and forces that we see around us. Now, this geometric language has rules, but it also has syntactical freedom like any language. And that requires some notion of a chooser to choose the free steps in the language. Now, the notion of randomness doesn't work so well when it comes to codes because meaning starts to break down. Besides, there's no decent experimental evidence for randomness in nature in the first place. A universal collective consciousness is one answer, but that sounds new age and religious. Now, nowadays, a good number of physicists discuss the idea that our whole universe is actually a code-based simulation in some fantastically powerful quantum computer in another universe. Now, if true, then by the same logic, that other universe where the computer running the simulation of our universe would also supposedly be a simulation in another universe. So the idea is a little shaky, but it's being discussed seriously by a lot of credible people. But it turns out that a universal collective-like consciousness of some sort may be physically inevitable. Now, we don't need to anthropomorphize this idea or make it religious or spiritual. To follow why, let us start with the idea of the collective behavior of cells in your body, each a single-celled microbe living its life. A long time ago, only this sort of cellular life form existed here on Earth. These little guys were not too smart, but they did choose what direction to swim and could chase nutrients, reproduce, and run from dangerous things. They made choices with their very simple systems of environmental awareness and desire to survive. Then they self-organized into colonies that were smarter as a group and had more environmental awareness than the individuals. Eventually, animals such as humans emerged. Sophisticated forms of awareness and consciousness now float on an ocean of 37 trillion living cells, self-organized as a human being. It is specifically the laws of physics that caused electrons and quarks to self-organize into 81 stable atoms, and from there, into human consciousness. And physics places no upper limit on the amount of energy and matter that can self-organize into conscious systems.
Physics allows the possibility of all the energy in the universe to eventually convert into a single conscious system that is itself a network of other conscious systems, a massive, technologically based collective consciousness. Given enough time, anything that can happen will eventually happen. By this axiom, this system of universal consciousness has already emerged somewhere in the frames of space-time ahead of us. Because it is possible, it is inevitable. In fact, according to the evidence of retrocausality time loops, that inevitable future is co-creating us right now, just as we are co-creating it.
Visit quantumgravityresearch.org to get more information.
Let's continue on into three that go for about 9 or 10 minutes each. The first is the Arecibo message, then on to the NASA crawler, and then the rocket exhaust and what comes out the back end of a rocket.
Now, you may already know what Arecibo message is and how it was actually sent in early 70s by several really famous people, including the famous Carl Sagan, who was pretty much the brains behind the entire message. And for the most part, it is a pretty interesting way of trying to send an encoded message to potential extraterrestrial life to see if they can reply back to us. But the only thing about this particular message is that it was really never intended as a kind of a communication, as much as a test of technology. So the main purpose for this message was really to see if we can actually pull it off. And it basically used state-of-the-art, by those standards, telescopes, which is the super famous Arecibo Observatory, that's in Puerto Rico. And it also used all of the scientific knowledge we had by then, including things like biology. But here's the thing though, most people don't realize that back then we didn't really know about DNA very well, and we didn't really know about the various proteins and various really interesting things happening inside your cell that we know today. And so for the most part, the message was actually relatively simple, but also kind of hard to decode because of how the message itself was laid out. And there's actually a really cool video about this that I'm posting in the description below. This is by Lemino, a YouTuber from Sweden, who talks a lot about the idea of sending messages. But there's one message specifically that nobody really talks about. The message that was also sent from the Arecibo, but was actually kind of done, in a sense, illegally and not with the scientific community approval. It's something that I briefly wanted to mention, and I really suggest and also encourage you to read more about it, because it's a really cool story of how some people will go outside of their comfort zone and also outside of the boundaries of, I guess, law, in a sense, to try to follow their passion and to maybe try to communicate with the extraterrestrial life. And the story actually revolves around this very colorful character who is technically an artist, but at the same time works in Harvard Medical School and also is associate at MIT. He's a really cool guy. Joe Davis is someone that basically kind of really pushes the boundaries in a lot of things, but it's really this one particular story I wanted to talk about because you can read more about him in the description below. Now, this story is not particularly well known because for the most part, it was never really published because he actually used the government funds to send another message to space, and he used the Arecibo Observatory with the help from a few scientists to do so. And interestingly, it's really a story of passion more so than just someone doing something illegal. It's also a story of excitement and outside of the box thinking, and for the most part, is kind of inspirational, at least to me personally. I'm also going to link you the blog post where I discovered this originally that goes through a lot of detail on what exactly was done, but in essence, he decided that he wanted to send another message using Arecibo during the 35-year anniversary from the first message. He thought it would be a good idea to kind of commemorate this and proposed this message, but unfortunately the government refused, and he found a way to do it with support from other people. And although Arecibo message that you see right here was already quite detailed and had a lot of information in it, a lot of people thought it was maybe too much information and it was kind of hard to decode. Like, this is what actually was in the message, and it was supposed to represent all of these things in real life on Earth. So it would be very hard to interpret this, but also at the same time, it was sent into the direction of the nearest globular cluster known as M13. That's a few thousand light years away from us, and it's somewhere right here. So we're going to try to take a look at it. Let's actually jump to it right now just to take a look at it. And essentially the reasoning was that if you send it toward a cluster, because there are so many stars here, the chance for having one with potential life on it would be much higher. But the arrival date for this is like year 25,000 or something, so we are not expecting to get any response back, at least not in the next few thousands and thousands of years. So he wanted to do something more practical. He wanted to send it to nearby stars that have potential for having habitable planets. 3 stars were proposed. First one is Gliese 83.1, which does have several planets around it. Then the second star is Kappa Cettae, also known as 96 Cettae, that also potentially has several objects that could be habitable. And lastly, the third object is the Tea Garden star. All 3 of these are actually relatively close to our planet and have very high chance of having Earth-like planets. Now, for the most part, it would only take a few decades to potentially get a message back from these particular objects. And the message that was sent back in 2009 is going to actually reach the brown dwarf Tea Garden star in 2021. So this is actually going to be the first star system that we're officially going to be able to send a message to. So this is a brown dwarf, and it might have quite a lot of terrestrial planets around it. We haven't really confirmed any planets just yet, but chances for having these planets is very, very high. Next question that Joe Davis had to ask is, what exactly are we going to send them though? How are we going to tell them that, hello, we're here, we're intelligent, we would like to communicate? And that's when he looked into biology, and his experience at Harvard came quite handy, and they decided to send, well, this right here. This right here is known as Rubisco, and this is why this message is known as the Rubisco message. And this here is considered to be the most prevalent, but also the most useful protein on the planet, produced by plants. Now, this is kind of what the actual protein looks like when it's assembled. And if you've studied biology in high school, you probably know what it refers to. Rubisco is actually responsible for fixating CO2 and then producing energy in a sense. So it's used during photosynthesis. Here's actually a very simple animation that shows you how Rubisco is used to fixate CO2 and to produce energy-rich molecules. Now, it just so happens that Rubisco is most likely the most abundant protein on the planet. We're not entirely sure, but we think so, because pretty much everything that uses photosynthesis has it inside. And although back in the 70s when the Arecibo message was sent, we didn't unfortunately know that much about biology back then. and thus couldn't really explain things as well as we can today. And that's why it makes more sense to actually send something related to genetics and related to actual biology. And most importantly, instead of sending several messages like we did with a Arecibo message, we would only send one single thing, which would be Rubisco, whose genetic components look like this. We know the actual nucleotides really well. We also know pretty much everything about it today. And there's just over 1,400 letters here. In other words, we needed to send a message that's about 1,400 characters long. And to send the message, what they did was convert every single nucleotide letter into a sound, and then this sound would be sent over the telescope into space. The actual sounds, because Joe Davis is an artist, were not just beeps or anything. He actually made words. Like, for example, the sound corresponding to adenine was know yourself. Then the sound corresponding to thymine was the. The sound corresponding to guanine was riddle of life, and finally the sound corresponding to cytosine was I. And in essence, when they literally converted everything here to sounds, it kind of sounded like this. So A becomes know yourself, T becomes the, G becomes riddle of life, and so on. So these sounds were then taken, and the idea was to send them across the space using the telescope. But unfortunately, there were once again some difficulties, and they actually had to use the smartphone from Joe Davis, specifically his iPhone, to try to convert these letters into sounds. And to send the actual messages, they literally used his iPhone. In other words, this guy now possesses one of the coolest iPhones out there that could potentially be responsible for reaching extraterrestrial life and sending them messages. But one of the coolest things about this story is that now there is a 75-minute long message that literally describes one of the most prominent proteins on our planet that's sent from an iPhone headed toward this particular planet in space. If there is anything there, and if they actually are able to decode the message and possibly send their own version of it back to us, we're going to find out, I guess, in about 10-ish years? Actually more like 13 or 14 years, assuming they can send it back right away. But of course the chances are that we're never going to hear back anything from either one of these planets. I think it's the idea itself that's really interesting to ponder and to think about, because we've always been trying to find something or someone out there that's not just us. The idea of finding alien life and the idea of finding extraterrestrials that we can talk to is, in the words of Arthur C. Clarke, kind of scary. Two possibilities, right? Either we're alone or we're not, and both of those possibilities are kind of terrifying. If we're alone, that means that I guess we'll never find anything, but if we're not alone, maybe it's not a good idea to keep screaming that, hello, we're here, and here's the code for one of the genetic components in the molecules that we have on the planet. There's actually, I think, about 2,000 various messages that various governments and also various individuals sent to space. And for the most part, as you know, we haven't really heard back.
This is NASA's largest and heaviest rocket, the 16 million pound Space Launch System and Mobile Launcher. And while it looks like it's not moving, it's actually being transported to the launch pad. It's just moving incredibly slow, at just 1 mile an hour. To get it to the launch destination, NASA uses this, the $144 million NASA Crawler Transporter. Large enough to almost fit a professional baseball infield on top, it's the largest self-powered vehicle on the planet. And it's a key component to the Artemis program, NASA's most ambitious mission yet. Every long and complex journey into space starts with this slow 4-mile journey to the launch pad.
It's the first time that we will be carrying the full mobile launcher and the vehicle stack out to the launch pad. It's an integrated test to check out all the systems, so it's very important, and we're all working very diligently to make sure that it goes well.
The crawler transporter is so massive, it takes a crew of 25 to 30 trained engineers and technicians to operate it.
You have a driver and a backup driver, engineering responsibilities in the control room. You've got gel operator, which is our jacking, equalizing, and leveling system that keeps our load level. Then you've also got technicians in the engine room. You've got technicians in the pump room. You've got technicians roving around the catwalk, keeping an eye on all the hydraulic systems, as well as you've got people walking on the ground all around the crawler, keeping an eye out. They have a better vantage point than the driver, so they're in constant communication of how things look on the ground, where our trucks are pointed.
Drivers operate the crawler from one of 2 driver cabs located on opposite corners of the vehicle. Instead of reversing, the driver walks to the opposite cab to continue to steer the vehicle.
This button is what we use to acknowledge that our cab is in control. The lead engineer in the control room will actually go assign a cab control, and then the driver, whoever's in the cab, will acknowledge the command from this button. These 3 will let you choose your steering mode. So most of the time we're operating in great circle, which means the front cab is controlling all 4 trucks, and the crawler will actually turn in a big circle with the steering mode in the center.
It'd be one thing if the 4-mile journey was a straight line, but it's actually curved. And turning the crawler is one of the biggest challenges.
The crawler can only steer up to 6 degrees. So we've divided the steering wheel into 1 degree increments, and so we can have a visual representation of how much we're steering. Driving on curves involves a lot more anticipation. You have to get your turn in early. You put your turn in, and then you have to wait a little bit before you actually see the trucks react.
The crew is responsible for transporting billions of dollars worth of research and development, so every crew member must have a full understanding of the crawler's systems and its 70,000 individual components.
So you see that right, see the wear here? It's the same on the outside. See, it's not wearing down here, but you get that wear there.
To become certified to drive, it depends person to person, but usually it's somewhere around 1.5 to 2 years.
While many different rockets have sat on the crawlers over the years, the crawlers themselves have remained the same.
The 2 crawler transporters we have in our fleet have transported every single launch vehicle from this vehicle assembly building out to pad complex 39A or B since 1965.
The Marion Power Shovel Company built the crawlers in the 1960s by adapting its mining equipment and used 2 locomotive engines to carry up to 12 million pounds.
And with the extensive maintenance done over all these decades, we've kept this thing running, in some cases as good as it was new.
In the past decade, the crew has adapted 1 crawler transporter to increase its carrying capacity for the SLS.
These are called our traction roller assemblies. This is what supports the entire weight of the crawler. These trucks will constantly spin all around this, and these will support everything, including we put the rocket on top.
When we started replacing these 88 roller bearings, we did them in 1 truck at a time, so that would be 22 at a time. Then we took it out for a test run, and that would be 6 months worth of work there.
In total, it took 5 years just to upgrade and test all 88 bearings.
Before the upgrade, they were originally designed to carry 12 million pounds. And now with all of our upgrades, we can carry at least 18 million pounds.
Inside the crawler, the vital systems that run the vehicle sit inside the engine room.
So behind me here is our Alco engines. They're 2,750 horsepower. These engines are original to the crawler. I mean, they've never been replaced. They're one of the few still remaining things from the original NASA program. And this is our Cummins AC generators. These provide AC power for all our onboard systems, including our motors for our pumps, our fans that you're standing directly below here to actually introduce clean, cool air into the engine room for the techs that are in here.
Today, the crawler is making its way from the crawl yard to the vehicle assembly building, where it will pick up the SLS and mobile launcher for the first time.
If anything doesn't feel right, if anything doesn't look right, or if something's not right, stop. Bring the crawler to a stop.
After a briefing, the crew inspects every inch of the crawler before they get the all clear to start the engine.
We check all the different pins, cotter pins, quarter stocks up that holds the track together. We check every single one of them on every single belt just to ensure that they are there, because we don't want to break a belt on the way.
With everything in working order, the journey to the VAB is underway. Engineers and technicians walking alongside the crawler, referred to as walkers, are responsible for flagging any potential issues to the rest of the crew.
I'm checking the gear case pressures. It has to maintain, a certain pressure in order to function properly, otherwise you'll get an overheat. You're doing an overall check of the whole crawler just to make sure that everything is hunky-dory so we can get to where we're going.
As the crawler nears the VAB, the driver begins to bring it to a stop.
We are slowing down our speed pot, bringing the crawler to what we call a normal stop by just dialing back, slowing down gradually, giving all of our systems an opportunity to adjust and just slowly come down.
It takes about 14 crew members to plug its power cable into an outlet for shore power.
We always like to keep our systems running like a computer in your house. You don't shut it off every time you use it, it just goes to sleep. So all of our electronics are that way, they go to sleep. And then we have certain types of heaters that keep our engines kind of lukewarm all the time so they're not starting cold. So that always needs to be powered.
These last steps ensure that the crawler is set up for its ultimate task, receiving the SLS and mobile launcher. This roll to the launch pad will test all the work the crawler team has put in over the past decade.
The crawler actually crawls or traverses underneath the vehicle and the mobile launcher. Once we're positioned correctly underneath these gel cylinders, we jack up, lift up the whole vehicle off the mounts.
With the rocket secured on top, the journey to the launch pad begins.
The ground's not always flat, so we have this jacking and equalizing and leveling system that we use to maintain level throughout the transport of the Artemis vehicle. We have an automated system that actually kind of keeps track of our parameters. When we're going up the slope itself, we have one end of the vehicle jacked all the way down, the other end is jacked all the way up, so we've got a range of about 5 feet.
Ahead of the crawler, a truck sprays about 30,000 gallons of water onto the rocky path, which the crawler pulverizes as it inches towards its destination.
The rocks that we roll on, as we crush them, it creates dust. These motors below us here suck in a lot of air to keep them cool while we're rolling, so that dust will get caught up in those filters and they'll clog them up. So by wetting all of the rock, that keeps the dust level down, and then it also changes the friction on the rocks, so it makes them easier for us to turn.
It ultimately takes 10 hours and 28 minutes for the crawler to reach its destination, where it finally lowers the SLS onto the launch pad. The SLS will remain at the pad for a 2-day wet dress rehearsal, where the team will run through the countdown and other procedures. No matter the mission, every long and complex journey into space starts with this slow 4-mile journey to the launch pad.
It's not a piece of flight hardware, it doesn't get all the fancy press that the launch vehicle does, but in the background, we're the most important piece of equipment.
Hello, it's Scott Manley here, and this video sequence, as you can guess, is the business end of a space shuttle during ignition and launch. It's actually from a video called Ascent, which has an amazing amount of technical commentary, and I highly recommend it. But the reason I'm showing you it is because people ask me regularly, why does a specific rocket look the way it does? Specifically, the exhaust. And with the space shuttle, you had this amazing contrast between the RS-25 engines burning hydrogen and oxygen, and they were practically transparent. Meanwhile, the solid rocket boosters that provided most of the thrust at launch produced this intense white smoke. The main engine exhaust is optically thin because it is mainly gas, water vapor. The solid rocket boosters, the exhaust contains a huge amount of particles from the propellants. The fuel in the solid rocket boosters is ammonium perchlorate, aluminium, and it's all bound together using something called polybutadiene acrylonitrile. All this stuff is mixed together at the factory and ignited at launch time. One of the products that comes out is alumina. That's basically aluminium oxide, and it will condense into tiny little drops. That's basically the smoke. But also, because it's mixed together, the mixing isn't always perfect. It's not totally homogeneous. You'll have grains where you sometimes have too much oxidizer, sometimes you have too much aluminium. And that means that the grain can actually continue to flow out, and in some cases it is still burning as it leaves the nozzle. So let's come back to the RS-25 engines. First of all, the exhaust is pretty transparent because the temperature is so high that the water, which is the exhaust product, simply won't condense in time. But there's another even more interesting phenomena to note here, and that is those hot spots in the exhaust. These are called Mach diamonds or shock diamonds, and are not exclusive to the space shuttle. You've probably seen them in many different kinds of engines. Here's a fine example in the afterburners of an SR-71B. Now what's going on here is the rocket exhaust is actually lower pressure than the air around it. And that may seem very strange because you think of rockets being very high energy, high pressure systems. But in fact, what rockets are trying to do is throw the gas backwards very fast. And in the reference frame of the exhaust, the pressure could actually be lower than the atmosphere around it. So as the gas leaves the nozzle, it finds the ambient atmosphere squeezing it inwards, whereupon it eventually gets squeezed down so far that it's now higher pressure, and so it begins to expand back outwards. And so you get a series of oscillations, and that's why you see multiple shock diamonds coming out of an exhaust. Now I have a whole other video on rocket nozzles, but the basic rule is you want the pressure of your rocket exhaust to be exactly the same as the ambient pressure where it's firing. Now the space shuttle engines, they have to work from all the way at ground level all the way up into orbit, so they actually want to be wider so that the air exhaust pressure is lower. So to allow them to operate most efficiency at vacuum, they are wider than they should be. They are overexpanded. And as a consequence, when the exhaust gases leave that engine bell, it quickly gets squished down and it produces those three very obvious compression zones. And if the imagery is right, you might see even more. Now, I'm not going to go deep into the science behind the colours of light coming out here, but there are two main mechanisms. The first is black body radiation, and that requires a body. It requires small particles in the exhaust. In the case of the solid rockets, you are getting alumina. In the case of things like kerosene, liquid oxygen, you're going to have some particles of soot forming. So those particles will be at the same temperature as the rest of the exhaust gases, and they will emit like a black body. Whereas the gas that makes up the exhaust from the main engines, that is not a very good black body radiator. Instead, it emits this blue light, which is associated with chemical reactions. In particular, I think it's down to the hydroxyl groups interacting with hydrogen to create water. But many of you will know the Delta IV and its epic launch fireball. You'll also note that the engines on the Delta IV produce an exhaust which is much deeper, much more intense than the Space Shuttle main engines. And that's because the engines on the Delta IV were designed to be much cheaper than the Space Shuttle's engines. The Space Shuttle engines are actively cooled by running liquid hydrogen through the nozzle, whereas in the Delta IV, they are made from graphite and they are designed to ablate during the heat of combustion. That means that ablating material, that carbon, is entering into the exhaust and making it bright and easy to see. It's also that you can see the interior of the nozzles in this case because they are allowed to rise to much higher temperatures. The interior of the Space Shuttle engines look just simply like metal because they are being continuously cooled by the flow of hydrogen. Which I guess kind of neatly brings us to this early test of the Merlin engine. This is using an ablative nozzle, but it's using kerosene and liquid oxygen. In this case, there's a lot of carbon in the fuel itself. Kerosene, or RP1, generally contains carbon chains of about 12 to 15 carbon atoms. And while the combustion is fast, it's not fast enough to burn up everything before it completely escapes the chamber. So between these secondary reactions and the soot, you get a very intense exhaust. And as something of an intermediate, here's a proton rocket. It's powered by a hypergolic mixture of dinitrogen tetroxide and unsymmetrical dimethyl hydrazine, which is a very long word, but the molecule is a lot smaller than your typical hydrocarbon chain in kerosene and requires less energy to break down. It's much more desperate to react with the dinitrogen tetroxide, and therefore you get more complete combustion and a less intense flame. And I guess the final logical step in simplifying molecules is methane. So this is SpaceX's Raptor engine that's supposed to power their BFR. It's in development right now, and it runs on methane and liquid oxygen, which means that it, again, has more complete combustion than their Merlin engine, so the exhaust is much more transparent. It also has these beautiful shock diamonds in there to look at. And while we've got this footage up, let's talk about one case where the colour of the exhaust really is a chemical signature. So when the engine starts up, it produces a bright green flash, and this is because they're using a pyrophoric ignition fluid called triethylborane. And it's the boron in here that produces this beautiful green chemical signature. You can actually see the green when the engines reignite during Falcon 9 landings, and sometimes during second stage ignition it's possible to see these. Now let's switch over to another even more classic rocket, one which I do get asked questions about. So this is the launch of a Saturn V, most powerful rocket in the world, powered by 5 F1 engines. These burn kerosene and liquid oxygen, and as their engines clear the flame pit, you're going to notice something very interesting. Now you can see the black of the engine bells, you can see the intense bright flame, but there's a section between the end of the nozzle and the start of that flame where the exhaust seems to be dark compared to the rest of it. What's going on here? Again, this is a consequence of the nozzle design. To keep the nozzle extension cool, instead of having it actively cooled by running liquid oxygen through it, what they did was they ran a lower temperature gas along the outside wall, and that gas would protect the wall. This is called film cooling, and the place they got the cooler gases from was the turbine exhaust. They would take the output of that, which would be fuel rich to keep the temperature low, and they would run it out there, and because it was fuel rich, it would be very sooty and very black, and it would also be cooler. So that's why it looks black when it's coming out, because not only is it a lower temperature, but it's also optically thick, and it's stopping the light escaping. The other thing to note is that as soon as the gases exit, because they're fuel rich, they do want to catch fire, and there's actually a flame front running up the side of this dark, and it's basically chasing upwards all the time, but the exhaust is moving too fast for the flame front to catch up. You can get a good idea of the plumbing in this cross section here. Now, the F1 isn't the only engine that uses film cooling, it's just one of the best examples that we have in terms of visuals, where you can see the very dark, cold gas. Well, it's cold, it's about hundreds of degrees centigrade, rather than the core, which is thousands of degrees centigrade. And it gives me an opportunity to play a few more seconds of this awesome launch sequence. Who doesn't love the Saturn V? Now, you've probably guessed by now that unlike the hydrogen-oxygen flame, this is a kerosene and liquid oxygen environment, so it's producing soot, and those particles that are in the exhaust make it a much better black body emitter, which is why the exhaust does emit so much more light than the pure hydrogen flames of the space shuttle. There are, of course, other combinations of rocket fuel which produce brighter or darker exhaust, but generally it comes down to how big the molecules and particles are that are condensing in the exhaust. All of the examples I've shown so far have been at ground level, but of course as the rocket moves up through the atmosphere, there's another effect that kicks in which changes the way the exhaust looks. Now remember I said that the shock diamonds were because the rocket engine was producing gas that, although it was moving fast, was at a lower pressure than the air at sea level. As the rocket gets higher and higher, the pressure drops, the outside pressure drops, and therefore the exhaust will begin to expand outwards. And so instead of this tight stream with the shock diamonds, it becomes this giant wide fan-shaped exhaust, or in the case of the Falcon 9, it begins to resemble a flower if you ask me. Now in the case of the Falcon 9, because a lot of the light is coming from soot heated by black body radiation, as the exhaust expands outwards, that means that it's actually cooling down. So the exhaust stops emitting light, and in fact, as it gets higher, will start to obscure light. So yeah, this has been a rough, high-level discussion and illustration of a few examples. I mean, rocket exhausts, they look amazing. You know, they're part of the poetry and the art of rocket science. But I think it also makes them more beautiful if you actually understand why some of these things are happening the way they do. I'm Scott Manley. Fly safe.
So we'll close with the launch of the NASA Tropics satellite, which they shot up 2 of them. Each of them had 2 pairs of satellites on board. They were principally for hurricane and cyclone monitoring. This was fired off from Rocket Lab's launch site in New Zealand, shown on the map there on the eastern side of the North Island of New Zealand. Rocket Lab is the one where they try to catch it, or have tried to catch it by helicopter when the bits come back down afterwards, and that was shown in a meeting quite a long time ago now. Now, the name of the rocket that they're firing up on this first launch was Rocket Like a Hurricane. So a strange name for a rocket, but that's what they actually christened it. The second one has already gone up, and you'll notice a couple of things as it launches from New Zealand. First of all, it'll pass through the point of max Q, which, if you were here for last month's meeting, is the point of maximum aerodynamic pressure. So the maximum stress actually on the rocket occurs at the point of max Q. And after it goes above that, they can throttle the rocket up to 100% of its power. And as the previous video indicated, the exhaust at that point starts to fan out into like a flower shape, and you'll definitely see that from the onboard video as it goes up. Notice also the colour of the nozzle indicates it's getting very, very hot as it goes up. And of course, being launched in New Zealand, you might be able to guess what colour everyone was wearing in mission control, and you'll see that at the end as well. The background music to this is Sirius, put together by a Swedish composer known as Infraction. And it goes for a couple of minutes and then we'll close. that you saw one of the satellites come out one side, the other one was jettisoned out the other side as well. So all four of those are out and active now. And with that, we'll close the September meeting.